standard technique in numerical methods which says that if you have a second order equation which is of this form, see here, I need to write, so previously the equation was mq double dot plus c plus g equals star. We need to write it as q double dot, so hence we need to invert this, m inverse t minus c minus g minus friction. Okay, so if the mass matrix was not invertible, I couldn't do this. But again, mathematically we can prove it is always invertible because it comes from kinetic energy. Kinetic energy is always positive. Okay. So what do we do? Instead of this, MATLAB doesn't understand. We define a set of new variables which is x1 to xn, which are nothing but q1 through qn, and another n variables xn plus 1 to xn to n, which are q1 dot and qn dot. So this is sometimes called a state space formulation. So you have position and velocity as two new variables. Instead of using acceleration, you say q and q dot. I write the differential equations in terms of the. If you were to write this, you can write it like this. So basically you have converted n second order equation into 2n first order equation. This is a very standard technique in numerical methods. Okay, and hence I can go to MATLAB, give whatever is this right hand side with some initial conditions. Okay, all numerical methods need some initial condition to start with, and then you can just go and solve. How about parallel robot? Again, very quickly, all you need to do is just modify the right hand side. So it's a little bit more complicated, and maybe tomorrow it will be dealt in more detail. But it can be done. So you should not worry that it cannot be done. Okay, so let's do some simple simulation. So this is a robot, 2 degree of freedom robot with again the same numbers. And what do we want to see? We want to see first, we want to make sure that our program is correct. The program is doing correct things. Okay, so we give some initial condition which is θ1 is minus 90, θ2 is 45, and we don't give any torque. Okay, so this is like a robot which is hanging down like this, and then you lift one of them by 45 degrees and leave it. So what do you think will happen? So it will start oscillating. Okay, it will start moving. Okay, and we want to see whether whatever the motion is happening makes sense or not. First thing is to make sure that whatever you are doing makes sense or not. Okay. So if you were to take this to MATLAB and plot, you will see one θ1 plot looks like this, θ2 plot looks like this, and the tip, I'll show you some videos a little later, the path traced by this tip looks like this. Okay, so there is some damping included in this, hence why it is dying down like this. But one of the natural question is, see in this, so in this robot there is no torque. Okay, I am not applying any motor, is not applying any torque. Okay, I have just given some initial displacement to the second link. So the first natural question which should occur is, why should the first link move? Okay, there is no external force which is acting, no motor torque. The second link is just given, and there is only gravity. So why should I get a plot of θ2 like this? Okay, so θ2 is like this, why should θ1 change? Okay, and this is what happens when you have nonlinear coupled ordinary differential equations. So even if there is no external force, because the two equations of motions are coupled, if anything happens to the second one, first one will also move. Okay, and this is sort of, tomorrow we'll see that this is a big problem in control. So I want to make only one link move. Okay, I apply some motor torque to that link. Okay, because of that motion of that link, some other, maybe the second link, yeah, I am trying to move the last link of the robot. I am trying to orient to some object. So the first link will also start to move. Okay. because all these equations are coupled. So your controller has to make sure that is what is happening. Okay. So let's see whether we can see some of these movies or not. Sorry. Okay. This is not the real one. So you can see that initially it started off somewhere, and then the path traced by the tip is very, very strange. It is moving in some very strange way, which is not obvious. Why should the path be like this? But this is what the equations of motion are telling you. Okay, so you can just do it once more. So it is starting from some initial condition vertically down with some 45 degrees, and the path traced is this way. Okay. So this is what I will do now. So this is the basic lecture, but I thought I will show you some other things which you can do with this. Okay, and what some serious dynamics issues, some serious dynamics problems which you can solve. So just let's summarize this, and then I will show you some more nice simulations. So if you have any serial robot, you can obtain the equations of motion using Lagrangian formulation. You can solve inverse dynamics. You can solve forward dynamics. Okay, inverse dynamics is very, very straightforward. You just substitute. Okay, whereas forward dynamics involves numerical simulations, and this is what I want to discuss a little bit. So not everybody writes equations of motion and solves them using MATLAB. It is not required anymore. Okay, so there are these software packages which are available, there is one called Adams. How many of you have heard of Adams? Okay, so there are these software packages which are available called Adams, where you can actually draw your robot. Okay, you can put, say this is the material, this is the geometry, and then you can ask it to simulate. Okay, so just 1 minute. Just 1 minute. So just some few minutes. Is that okay? So I want to show you